So for this problem, it says prove proposition 1.2.10, which is let x of D be a metric space, let E be a subset of x, and let x naught be a point in x. And the following statements are logically equivalent. A. X naught is an adherence point of E. B. X naught is either an interior point or a boundary point of E. C. There exists a metric sequence x of n equals 1 to infinity in E, which converges to x of naught with respect to metric D. So with these two definitions, I can carefully define these three sets. First, interior of E, exterior of E, and the boundary points of E. And it's pretty trivially seen that these sets are mutually exclusive. I can also as well define the set of the adherence points, which is defined as E bar, as such. So first, proving A to B. Let's just let x naught be an adherent point of E. We want to show that x naught is in interior E union with the boundary points of E. So the first case is x naught is in the exterior of E. So should we know that interior of E and exterior of E and the boundary points are mutually exclusive? For sake of contradiction, let x naught be in the exterior of E. Since x naught is in the exterior of E, this basically implies that exists R greater than 0 such that there's a ball of x naught comma R intersected with E is equal to the empty set. X naught being adherence points, though, implies that for all R greater than 0, the ball of x naught comma R intersected with E is not equal to the empty set. Thus, there's contradiction here. And so this can't happen. How about we do the opposite case, right? X, which is not, X excluding the exterior points of E, which, as we know, since these two sets, since the exterior E is mutually exclusive to these two other sets, this is equal to the union of these two sets. And since we know this is going to be in the complement of this, we can basically take the opposite of the definition of the exterior points, which is for all R greater than 0, the ball of x naught comma R intersected with E is not equal to an empty set. And thus, x naught is an adherence point of E. For B to A, let x naught be in the interior of E union the boundary points of E. And we want to show that x naught is an adherence point of E. So the case is let x naught be in the interior of E. And so there exists R1 greater than 0 such that the ball of x naught comma R1 is a subset of E. And since for all R2 greater than R1, this ball that we have here for R1 is contained in this new ball of R naught comma R2. And thus for all R2 greater than R1, this ball of x naught comma R2 intersected with E is not equal to the empty set. And we know that this is true because this ball for R1 is always contained in here. And so any intersection with E with this R2 contains this. And since this contains a non-empty intersection, we know that this contains a non-empty intersection as well. And therefore, for all R is greater than 0, remember, since R2 and R1 is both greater than 0, there exists an R such that this ball of x naught comma R intersected with E is not equal to the empty set. So next case is x naught is in the boundary points. And so we basically know that these are complements between interior of E and the union of the exterior of E. And so we basically know that the complement of interior of E basically implies that for all R greater than 0, the ball is not contained in E, which isn't that important here, but for the exterior, we know here that the ball of x naught comma R intersected with E is not equal to empty set, which is what we want here, which is in here, because it's the definition of an adherence point. So for B to C, we simply want to, for these two cases, for interior of E and or when x naught is in interior E or in the boundary of E, we want to construct some sequence such that it converges to x naught in E. So in the first case, for x naught being in interior of E, let's just let the sequence of points just be equal to x naught. And so trivially speaking, that just means the sequence is equal to x naught, and then this is just equal to 0, when the limit of 0 is just 0 right here. And so that's it converges based on the definition here. For the second case, the boundary of E, when x naught is in there, This basically implies that since it's not in the exterior, this is the complement of the exterior set for all r greater than 0, this ball right here, intersected with E is not empty. So there exists at least some point in there. So let S not equal to some point in this intersection with this ball and E. And that's equal to like the midpoint of these 2 points intersecting. And so you kind of visualize this as I'm constantly finding the midpoint of the midpoint of the previous midpoint. Finding the midpoint of the previous midpoint here. And it's trivially seen that the limit of S's men is equal to x naught. And since the ball of since this intersection, this ball intersection with E, the subset of E, and this is not empty, there implies that there exists, or that for all n greater than 0, S of n is in E for all points in E, and thus the limit of this is equal to 0 in E. So from C to B, we basically want to prove that there exists a sequence x of n in E which verges to x of naught with respect to D, implies that x of naught is either an interior point or boundary point of E. So the easiest way to prove this is, for sake of contradiction, let's just assume that x naught of naught is not in the union of these two sets, which basically implies that it's since, remember again, these two sets are or the three sets are mutually exclusive, interior, boundary, and exterior. This basically implies that x of naught is, if not in the union of these two sets, is in the exterior of E. Since x of naught is in the exterior of E, this basically implies that there exists r greater than 0 such that the ball of x naught and r intersected with E is equal to empty set. Since the limit of n approaches infinity of the distance of x naught to n x of n is equal to 0, remember this is based on the convergence definition. This implies that for all epsilon greater than 0, there exists n greater in the natural number set such that the distance of x of naught comma x of n is less than epsilon for all n greater than n. And remember, this is the basic definition of a limit or convergence. And this basically implies there exists n in this natural number set such that d of x of naught comma x n is less than r. Remember, this is the same r that we constructed right here for all n greater than n, which basically implies that there exists an I greater than n such that x of I in this ball is not in E, which is a contradiction to what we assumed, and thus contradiction, x of naught has to be in the interior of E union the boundary of E.